Hello everyone, myself Ayush Koda SM studying in Sri Venkateswara College of Engineering. Subject Data Structure and Application, Semester 3 USN 1V 23 CS021. Topic Microstructural Studies of Friction Stir Welds. Subject Code BCS 304. Author Michael Stun and AP Reynolds. Agenda we are going to discuss is abstract, introduction, specimen and FSW process, microstructure measurements, microstructural studies, banded microstructure, relationship between fracture and banded microstructure, discussion of results, conclusion. Abstract. Friction stir welds in 7 mm thick 224 T351 aluminum rolled sheet material have been completed. Metallurgical hardness and quantitative energy dispersive X-ray measurement have been performed, which demonstrate that a segregated band microstructure consisting of alternating hard particle-rich and hard particle-poor regions is developed. Mixed mode 1-2 monotonic fracture experiments confirm that the observed banded microstructure affects the macroscopic fracture process. Since the band spacing is directly correlated with the welding tool advance per revolution, our results indicate that the opportunity exists to manipulate the friction stir weld process parameters in order to modify the microstructure and improve a range of material properties, including fracture resistance. Ever since BV introduction, the difficulty of making high strength fatigue and fracture resistant welds in aerospace aluminum alloys, example high yield to X7X series aluminum, has long inhibited the use of welding process for joining aerospace structures. Typically, mechanical fastening has been the joining method of choice, except in production of pressure vessels for rocket propellant and oxidizer tanks. Even in pressure vessel applications, heavy weld lines must be incorporated to account for the severe property knockdown resulting from the fusion welding processes. Many of the problems with welds in aerospace aluminum stem from the unfavorable distribution of brittle solidification products and porosity in the weld region. Friction stir welding is a relatively new technique for making solid state welds in aluminum alloys. Encouraging results have been obtained when FSW has been high on strength aerospace aluminum alloys that are typically difficult to weld. Friction stir welding was invented at the Welding Institute UK in 1991. Since that time, it has been introduced that the commercial practice in a number of applications. Although aluminum alloys may be joined using conventional fusion welding techniques, certain aspects of friction stir welds makes FSW extremely attractive for the joining of aerospace alloys. Of greatest importance in the fact that the process occurs in the solid state and therefore the formation of brittle solidification products is minimized and grain boundary liquefaction cracking does not occur. Heat input is in general significantly lower than fusion welding processes. In this work, a 1.22 mm into 2.44 m into 7 mm thick sheet of 2024 to T3 aluminum was cut into two square pieces. These were friction stir welded together using a tool with a 23.0 mm diameter, the shoulder, and 8.2 mm diameter pin. The measured processed parameters were rotational speed of 360 rpm and a travel speed of 3.3 mm perpendicular to the rolling direction of the sheet. Figures one shows a crown side view of a typical FSW used in this work. The tool contacts the crowd side of the FSW during processes, while the root side is in direct contact with the backing plate, and opposite to the crown side, the advancing and retreating side of the weld corresponds to locations where the maximum and minimum workpiece are observed. Microstructural measurements. To acquire to acquire high contrast images of each. So that is consistent in general character with previous observation at location 3 corresponding approximately to the edge of the welding tool spin. An abrupt transition from the highly refined equaxed grains comprising the nugget to deformed base metal grains occur at a location corresponding to approximately the tool shoulder radius on the advancing side. Location for a relatively coarse recrystallized grain structure is observed at 4.5 mm from the edge of the shoulder. The microstructure appears similar to the original elongated grain structure present in the rolled 2024 T351 base material. This finding indicates that the homogeneity of the weld microstructure may be modified by changing the welding parameters. For example, one aspect that band spacing will decrease as the tool advance per revolution is reduced. A smaller band spacing should result in a more homogeneous structure within the weld. However, the changes in the tool advance per revolution have ancillary effects on weld energy and hence local material properties within the weld. Relationship between fracture and banded microstructure. The crack grows almost vertically towards the advancing side of the FSW for a distance of 5 to 6 mm from the weld center line to a position near the edge of the welding pin. As the banded microstructure turns towards the load direction, the fracture path continues along the general direction of the bands until the crack direction is aligned with the loading direction at the point. Several small cracks initiated ahead of the main crack tip and coalesced along the path. The approximate the L direction of the weld. Once the crack has turned, it grows stably near the edge of the FSW along the advancing side. Discussion of results. The presence of clearly defined bands in the 2024 T351 microstructure appears to be due to the parameters chosen for the FSW joining process employed. The FSW process required rotational extrusion of material around the front of the tool. This extrusion takes place in very thin layer of material surrounding the tool and a large strain and strain rate gradients predicted. It is conjugated that the segregation of particles results from the entertainment of the particles in the region corresponding to high strain rate gradient. If the particles are large relative to the distance over which the strain rate changes appreciably, then the particles may tend to roll towards the low strain rate region, resulting in clearly defined bands of high and low particle density. Conclusion. A series of controlled friction stir welds have been manufactured using 6.255 mm thick 2024 T351 aluminum rolled sheet material, resulting from metallurgical hardness and quantitative EDX measurement clearly shows that the friction stir welding process can create a segregated banded microstructure consisting of alternating hard particle rich and hard particle poor regions. In addition, initial results from mixed mode 1-2 monotonic fracture experiment demonstrate that the observed banded microstructure affects the microscopic fracture process in the welded material, with the crack path tending to follow the regions of high particle density. Thank you for watching the video. Make sure to like the video.